Hello team. In the next few videos, we're going to talk about virtualization. And in this video in particular, we're going to talk about software emulation. So we have seen that virtualization is key in cloud computing. Virtualization allows cloud operators to share resources across different tenants and to isolate the virtual machines that they allocate to different tenants. And we're going to talk about three different types of virtualization. In this video, we're going to talk about software emulation. In the next videos, we're going to talk about power virtualization and full virtualization. In software emulation, we have a CPU A, say the CPU of a gaming console, and another CPU B, for example, the CPU on a PC. And we can virtualize A, like the video game console, by emulating A's operation inside processor B, like inside the computer. Classical examples of this are like console emulators, like SNES emulates the Super Nintendo Entertainment System, and this is a screenshot of SNES running Mega Man X. So in software emulation, what happens is the emulator reads one instruction from processor A, and then it runs multiple instructions on processor B to perform the work that the instruction from processor A would do, say instruction X. And this is what SNES does. So it reads the code that Mega Man X will run, and then for each instruction in Mega Man X's code, it runs many instructions on the Intel processor to emulate what the game would do. So as examples of emulations, we have gaming consoles like SNES we see on the slide. We also have bytecode interpreters that we're going to talk about next. And of course, we can emulate a PC inside another PC. And when we emulate a PC, see there's one instruction from the Intel processor, and if we want to emulate this instruction, we will need to do everything that that instruction does by hand. So we're going to have to use instructions to load the data in memory, to change the value of registers, and then do the computation, let's say if it's an addition, and then we're going to have to store the result in a different register. So each instruction that we emulate will take multiple instructions in the real hardware. A common type of emulator is a bytecode interpreter. So some languages compile to bytecode. They don't compile to native code like C and C++ do. They compile to an intermediate format that is called bytecode. For example, Java, when we compile the Java source code into a .class file, so the .class file is binary, but it's not native code. It's code for the Java virtual machine. And similarly, when a browser loads a JavaScript, for example, on a web page, it will compile that JavaScript to some intermediate format that the browser runs. And the same thing with Python files. So the Python interpreter compiles Python source code into Python bytecode. We can look for the PYC files in the directory, and these PYC files also contain bytecode. And then the bytecode is interpreted by another program. Say the Java virtual machine interprets Java bytecode, browsers interpret JavaScript bytecode, and the Python interpreter interprets Python bytecode. One advantage of using bytecode interpreters is that it's easier to port an application to multiple different architectures. So instead of writing a compiler and making sure that everything works on the second architecture, the only thing you need to do in this case is port the bytecode interpreter. For example, if we write a Python code, we can run it on Windows, we can run it on Linux, we can run it on Mac, and we can run it on different architectures. For example, there are Python executables for cell phones, so that's like ARM processors, and there are Python executables probably for Apple's M1 architecture. So we can get portability by just porting the interpreter. The applications do not need to be changed. One problem with emulators is that emulators are very slow. And this happens because each instruction from the original CPU, say from the Super Nintendo Entertainment System, may take many instructions on the second CPU, CPU B, to emulate. For example, if we have a gaming console whose CPU runs at 100 megahertz per second, and we have an Intel GPU that runs at 2 gigahertz per second, so the Intel GPU has a frequency that is 20 times larger than that of the gaming console. But if each instruction from the gaming console takes more than 20 instructions on the PC to emulate, then the game will run slower emulated on the PC than it would run on the gaming console directly. And this is just this big overhead that we get with emulation. So we usually don't emulate a PC inside another PC, because each instruction on the emulated PC will require many instructions on the underlying hardware to complete. So emulation usually incurs a multi-factor, like multiple times, 2 times, 3 times, maybe 4 times, depends on what's being emulated, slowdown. So there's this loss of performance. We won't go into details here, but one thing that emulators can do to reduce overhead is just-in-time compilation. For example, the Java virtual machine, when it starts running a program, it starts interpreting the bytecode, and then when it reaches a region of the code that runs very often, that's requires a lot of CPU time to complete, it will compile part of the code to native code, so that it doesn't need to emulate anything anymore. It just runs on the actual hardware. Then it runs much faster. So just-in-time compilation is a technique that emulators can use to convert bytecode to native code and improve performance.